Hello, everyone. Thank you for that introduction. I'm Prajwal Sharma. I also have a co-author with us today. Krishna is here, and Vinay, who is also working in similar areas, who can probably help us in the discussion regarding the paper. Development paper is regarding the development of minimally invasive ventricular assist device. So the contents of the presentation is going to be like this. So the introduction is VADS. VAD is a ventricular assist device, which is mainly used to substitute the failing heart, and it is to provide temporary functioning of the heart during surgeries. Mainly, if you look at the traditional VADs, how is it? It's a connection, a bypass from your left ventricle to the pulmonary artery and the right atrium. But here the motivation is there any other way to design a VAD is what the question was to Dr. Vikas, who was one of the co-authors of the paper. And we put up the problem statement like this. VADs are mainly a ventricular assist device, which is a mechanical, electromechanical device, and it has certain problems over the past period of time. That is shortness of breath, hypotension, chest pain, bleeding, and so on. The main problem here is when you apply an extra pressure, there is a mean pressure difference between the atrium and the left ventricles. So the problem here is the blood can flow back to your ventricles. So what we defined is there any way so that we can push the entire blood from the ventricles towards your aorta or the atrium and make sure that it doesn't flow back. So the design of the problem statement goes like this. So this is the balloon that we are using. It's mainly the intra-aortic balloon pump. So these are your ventricles, the left ventricle and the right ventricles. There are mainly three kind of ventricular assist device. That's the left ventricular assist device, right ventricular assist device, and the biventricular assist device. We are trying to solve the biventricular assist problem. So we are wrapping the balloon around the entire ventricle, and we are compressing and decompressing the balloon according to the ECG signal. We have an inflation-deflation circuit which inflates and deflates this balloon. So this is your ECG. From R to T of your ECG, it's called the systole region where the balloon inflates and exerts the pressure on the ventricles of the heart. And this is the diastole region where the balloon deflates. That is when your heart, the ventricles expand and your balloon deflates. This is how we got the ECG. We're using an Arduino Uno, which is connected to a ECG sensor through a serial peripheral interface. And these are your three electrodes, which is connected to the right arm, left arm, and the right leg. So this is my ECG. I got my ECG. There is a bass wandering and some noise. So we used a bandpass filter to get a ECG that can be used for further processing. So this is how your inflation and deflation circuit is. We have a power supply using an SMPS, and there's a relay. There's an air compressor, reservoir, solenoid valve, and vacuum pump. This is a microcontroller that Arduino. This is a driver that is used to control your solenoid valve and two solenoid valves because there is need of voltage, higher voltage of 12 volts to control these solenoid valves. This is your heart, and this is a balloon wrapped around it. Velocity sensor is mainly used to calculate what is the pressure that is being applied on the ventricles of the heart. And this reservoir is mainly because when you pass air through the air compressor, at one point your solenoid A cuts off and there is the air flowing out during the decompression. And at that point, your air compressor will be on and you want some tank to store that air and give that sudden pressure to the heart ventricles. So that is where this reservoir comes into picture. So how it works is your air compressor is on, your solenoid valve is on during the systole region, your reservoir, through the reservoir, the balloon inflates, and during the deflation, your reservoir is on, your solenoid valve is off, your air flows out of this vacuum pump. So that's how the compression and the decompression of the balloon happens. So what is the amount, the volume of the reservoir required? This is the formula to calculate it. This is the volume of the tank. This is the pressure. This is the time for which your valve will be open. So this is approximately around 0.3 seconds. That is when your systole happens, the diastole happens. This is your capacity of the inflow and the outflow. This is the pressure. We are using a 260 psi air compressor. So P2 minus P1 is going to be 260. and this is your inflow and the outflow rate. We used around a 2 liter per minute air compressor. So C in minus C out becomes 2 liters per minute. So the reservoir that is required is 500 ml of reservoir. So the reservoir here is going to be a 500 ml reservoir. So this is our experiment that we calculated. This is the ECG that we acquired. This is going to be a R and T. This is the systole region. This is what I spoke about, the two valves, the valve A and the valve B. So when your valve A is open, that is when your balloon inflates. You see a graph here that is inflating. You see a ramp up here. That is when your inflation happens. You cut off the valve A and now your valve B is open. That is when it deflates. So this is when your heart actually compresses, the ventricle compress. There is a pressure applied on the heart. Your ventricle deflates. That is when the pressure drops from the balloon. So now the problem is, this is for the normal ECG. Now what happens when your ECG expands or compresses? That is when your delayed ECG. Here you might come after exercise, your heart rate increases, or you're in a rest, your heart rate decreases. We'll have to account to that as well. So this is the major problem that we faced. Now what happens in this case? Your valve is open for valve B is open for quite longer time than this. So more air is accumulated on the reservoir. So you see a pressure differential here. That is here, this ramp up, you see a pressure differential from the normal pressure that is applied on the heart to the one here. So to take care of that, we used, if I can go back to the main diagram here, we have this velostat sheet sensor. This velostat sheet sensor actually calculates what is the pressure required, and it gives the feedback to the microcontroller telling that, okay, we have reached the nominal pressure that is supposed to be applied on the heart, and we cut off the solenoid valves. That is why you see this graph up and down. You see this switch on and switch off of the solenoid valves. That is how you maintain the actual pressure. So now this is almost the same as compared to the pressure differential here. So this is when the other case, when you have an expanded the shortened ECG. This is how it. So we have done it for expanded ECG and the short ECG and the normal ECG. So the pressure that we acquired from giving that is around 6.44 mm of mercury and 3.3 mm of mercury, which is very small. The device is quite right now quite bulky, and the pressure that we are applying is quite small. So in the future work, we need a redesign of the balloon so that we can apply a larger amount of pressure on the heart, and the device has to be made smaller. We are using a huge air compressor now to give a small amount of pressure. So there is a requirement of redesign of the air compressor and the entire inflation deflation circuit, and the redesign of the balloon so that we can exert pressure only on the heart instead of the balloon expand on the both sides, right? Both inwards and outwards. So we need a redesign of the balloon where the balloon expands only on the inside, so that the pressure, all the air that we put into the balloon expands only on the inside, not the outside of the balloon. So this is the conclusion. We acquired the ECG and then used it for other inflation and deflation. So balloon which inflates and alternatively between promoting the pumping of the heart rate. We have a feedback circuit so that there is a cutoff whenever there is required, whenever we reach the nominal pressure. And the prototype gives you a pressure of 6.44 mm across and 3.3 mm during the systole and the diastole. I reiterate, this pressure is very small compared to the pressure that heart actually exerts. But if there is any suggestion that the audience can give us as to how can we exert more pressure with a better design, we are open for it. We are continually working on this, so we are open for suggestions. These are some of the references. Thank you. We are open for suggestions and questions.